Hello everyone. Today we are going to do a problem based on influence lines diagrams. Let us read the question one time. For the beam shown in the figure, draw the influence lines for the following: vertical reactions at A, B and C, shear at D, moment at B, and shear force and bending moments for this section. We have to use Müller-Breslau's principle. First, we need to find the number of segments. About the hinge, we have to find the segments. Here there are two segments, AD and DBC. You can see that for both of the segments I have given different colors. First, let us draw the ILD for the vertical reaction in the point A. From the point A, we have to remove RA and we have to apply unit displacement. The unit displacement should be applied upwards. Because of the unit displacement, the segment AD goes like this, but there is no change in the segment DBC. It remains the same. Let us see why this happens. The first rule states that the segments should remain straight. The segments should be always straight. Let us take the segment AD. Even though we have applied unit rotation, it remains straight. It is not curved like this. Also, the segment DBC remains straight. It is not possible that DB stays here, BC rotates. It is incorrect because DBC is a single segment. It can rotate altogether like this or like this. Even though it rotates, it will maintain straightness. But here it does not rotate. It remains the same. Let us see why. The second rule states that the vertical displacement in the supports will be zero unless given unit displacement. Only in the point A we have removed RA and given unit displacement, but still in the point B there is RB and in the point C there is RC. So in the points B and C the displacement will be zero. In this case, BC will be horizontal. We know that DBC is a single segment. If BC is horizontal, DB also should be horizontal. That is why in the point D, the displacement is zero. This is the ILD for RA. Now let us draw the ILD for the vertical reaction in the point B. We need to remove RB and then we have to apply unit displacement upwards. We know that the segments should remain straight. That is why when we give unit displacement, dB also going like this, the segment dBc should remain straight. We may have doubt why dBc is not going in this way. We know that the vertical displacement in the supports will be zero. In the point C there is RC, so the displacement will be zero. And in the point A there is RA, so the displacement will be zero. The hinge in the point D will go upwards and the segment AD will go like this. Now we have understood. Suppose DBC goes this way, the displacement in the point C will not be zero, there will be some height. We need to find this height. For the distance of 8 meter, the height is 1. So for 8 it is 1. But we need the height at the distance of 11 meter. So we have to multiply with 11. In this way we are getting 1.375. This is the ILD for RB. Now let us draw the ILD for the vertical reaction in the point C. We need to remove RC and we have to apply unit displacement in the point C. In the point B there is RB, so the displacement will be zero. Because of that the segment CBD goes this way. In the point D, there is a hinge. The hinge will go downwards and the segment AD follows this way. In the point A, there is RA, so the displacement is 0. These two angles are same. Using that, we can find this height. For the distance of 8 meter, the height is 1. So for 8, it is 1. But we need the height at the distance of 3. So we have to multiply with 3. In this way, we are getting 0.375. This is the ILD for RC. Now we are going to draw the ILD for the shear force in the point D. We need to give relative displacement of unity in the point D, left side downwards and on the right side upwards. But on the right side, we cannot move the segment DBC. We know that in the point B there is RB and in the point C there is RC. So the displacement will be 0. In this case, DBC will not move upwards. Only the segment AD will go in this way. Since there is a displacement on only one side, the displacement will be 1. In the point A, there is RA, so the displacement will be 0 here. Using that, we can draw this. So this is the ILD for FD. Now we are going to draw the ILD for the movement in the point B. Right now there are two segments AD and DBC, but we are going to find a value in the point B. So we have to split the segment DBC into two parts, DB and BC. You can see that for DB, I have changed the color. Now there are three segments AD, DB and BC. To draw the ILD in the point B, we have to rotate on both the sides of B. On the right of B, the rotation is not possible because here the displacement is 0 and in the point C also the displacement is 0. So BC will remain horizontal. We can rotate on the left of B. BD will go this way and the hinge will go downwards and AB will follow this way. If only one side can be rotated, you can keep these two arrows for reference. Using small angle rule, we can find this height. This height will be equal to the length of DB, which is 3. This is the ILD for MP. Now we are going to draw the ILD for the shear force and bending moment at a section 2 meter right of B. Now we have to split the segment DBC into two parts, DBE and EC. You can see that for DBE I have given different color. Right now there are three segments AD, DBE and EC. First let us draw the ILD for the shear force in the point E. We have to give relative displacement of unity on both the sides, on the left side downwards and on the right side upwards. Now on both of the sides there is a displacement. This height will be 1. Because of this, the point E will go upwards. Then we know that in the point C, the displacement is 0. So we can draw this line like this. In the point B, the displacement is 0. That is why it goes this way. Then the hinge in the point D move upwards. Then AD will follow this way. To find this height, we can use the formula A upon L. Here A is 2 and L is 8. 2 upon 8, it will be 0.25. To find this height, we can use the formula B upon L. Here B is 6. So 6 upon 8, it will be 0.75. These two angles are same. Using that, we can find this height. For the distance of 2 meter, the height is 0.25. But we need the height at the distance of 3. In this way, we will get 0.375. This is the ILD for the shear force in the point E. Now let us draw the ILD for the moment in the point E. In the point E, we have to give an internal hinge and we have to apply unit rotation. Because of the unit rotation in the point E, in this way, the hinge will go upwards. We know that in the point B, the displacement is 0, so the segment DBE goes this way, and the hinge in the point D go downwards. In the point A, the displacement is 0, so the segment AD goes this way. Also in the point C, the displacement is 0, so EC goes this way. In the point E, we have applied unit rotation. Both of the sides are rotating. In this case, this angle will be unity. We have to find this height. We can use the formula AB upon L. Here A is 2, B is 6. So 2 into 6 upon 8. We will get 1.5. These two angles are same. Using that, we can find this height. This is the ILD for ME. Now we are going to draw the ILD for the shear force and bending moment at a section 2 meter right of A. Let us keep this point as F. Now we have to split the segment AD into two parts, AF and FD. You can see that for AF I have given different color. Now there are three segments AF, FD and then DBC. First let us draw the ILD for the shear force at F. We have to give relative unit displacement in the point F, left side downwards and on the right side upwards. We know that in the point B and C, the displacement will be 0. So the segment DBC will remain horizontal. There will be no change. The segment FD will rotate like this and the segment AF will rotate like this. This total height will be unity. To find this height, we can use the formula A upon L. Here A is 2, L is 4. 2 upon 4, it will be 0.5. To find this height, we can use the formula B upon L. Here B is 2 and L is 4. 2 upon 4, it will be 0.5. This is the ILD for the shear force in the point F. Now let us draw the ILD for the moment in the point F. We have to apply an internal hinge in the point F and then we have to give unit to rotation. Because of that, the point F will go upwards. This angle will be unity. The segment DBC will remain horizontal. There will be no change. To find this height, we can use the formula AB upon L. Here A is 2 and B is also 2. 2 into 2 upon 4, it will be 1. This is the ILD for MF. Now we are going to draw the ILD for the shear force and bending moment at a section 1.5 meter left of B. Let us keep this point as G. Now we have to split the segment DBC into two parts, DG and GBC. You can see that for DG I have given different color. Now there are three segments AD, DG and GBC. To draw the ILD for the shear force in the point G, we have to apply unit displacement, left side downwards and on the right side upwards. We know that in the point B and in the point C, the displacement is 0. So GBC will remain horizontal. There will be no change. Because of this, DG will go like this. In the point G, we are only giving displacement. We are not giving rotation. That is why DG remains horizontal. In the point A, the displacement will be 0. That is why AD follows this way. Since the displacement occurs on only one side, this height will be 1. If this height is 1, this height also will be 1. This is the ILD for FG. Now we are going to draw the ILD for the moment at G. We have to give unit rotation in the point G. We know that on the right side we cannot rotate. DG will rotate like this. The hinge in the point D will go downwards and the segment AD will follow like this. Since we can rotate on only one side, this angle will be unity. This height will be 1.5. This is the ILD for MG. Now we are going to end this session. Thank you for watching this video.